Thank you, everybody. Thanks for coming. And let me introduce you to our lab. And I will speak for approximately half an hour. And afterwards, I will give the stage to Dr. Sebastian Scherer, coming from Carnegie Mellon, presenting their work there about robotic systems. But let me first introduce who we are and what we are doing here at the University of Nevada, Reno. So we created this lab, Autonomous Robots Lab. And I was thinking about the name. And the name was just where we want to arrive. So if you forget the lab, this is the goal. The goal of my research and the goal of, I hope, many people, and I believe to a large extent also the goal of many significant communities in our societies now, aim to develop the autonomous robot, multiple autonomous robots operating alongside with us, helping us with our work, and benefiting our society. There are many challenges involved, but through the way of developing technology, also the society has the potential to adapt and use robots in a positive way. But who we are. So I want to highlight that I'm the one that has the privilege to stand here and talk to you about our research, but the research actually happens, most of all, due to these people. So there is Dr. Christos Papachristos, a senior researcher that joined our lab from January 2016, from the very first month that this lab was developed. I joined the university also 2015 summer. Shehryar Khadak, he joined as the first PhD candidate of this lab, followed by Tung Dan and Frank Maskarich, who are now the 3 PhD candidates in our laboratory. There is also a research assistant at the graduate level, Tyler Sorey, who is not with us now because he's working at IGT, and also 2 undergraduate researchers that work with us at the moment. And as of this summer, we're going to have 1 more senior researcher and 1 more PhD candidate. And it's all about these guys that eventually do the work and make these results possible and allow, for example, me to come and tell you about how robotic technology can progress and make more autonomous systems. But before discussing who we are, the most important thing is what's the vision behind. And when I was a kid, I was happy that I read some of the book of this guy at the right bottom corner, which is Isaac Asimov. And he has all these cool novels about how robots are integrated into society, and they are very smart, and they can help us, and they can predict that they can harm a human, and they avoid it, and so on and so forth. So there are 2 parts of literature, people that predict a robotic some sort of dystopia, and this is the first book about robots and the first book that ever introduced the term robota, which means worker, and it was all about a robotic dystopia. But now, at least later in the history of society, there were people that envisioned that robots can work with us, for us, and in a harmonic way, in a synergetic way with us. And this is more or less also our goal. And to make robots ubiquitous, the key is that robots are able to operate autonomously. But what is autonomous? What is an autonomous robot? When we say an autonomous robot, or when we say a robot in general, we typically, most people that are not active in research or haven't really checked the latest videos on YouTube, they will think of a big manipulator that moves one box from one side to the other. This is a typical robot. That's a classical industrial robot. But robots now are much more than that. If you consider yourself, this is the ideal thing for a robot. You are able to enter an environment for which you have no prior knowledge, and you navigate in it with absolutely no problem. This means that, first of all, you can perceive the environment, and you can localize yourself in this environment. This critical task of localization and mapping, detection of objects, and understanding their relative locations against you, either they are static or dynamic, is the first critical loop of a robotic system for it to be autonomous. And we call that the perception loop. It's how we perceive the world. Then, if this is possible, if you know where you are and you know how the map looks like, if somebody tells you where to go, the second important skill you have is locomotion. You are able to go from A to B in a way that is robust and reliable. Even if there is a disturbance, for example, a rock, you will either overcome it or walk through it, and you can have no problem. Similarly, for a robot, ground or aerial, it has to be able to go from A to B in a robust and reliable way. And if we have these 2 fundamental tasks, if we can know where we are, and know the environment around us, and we can also go from A to B. The next question that remains is, all right, how does the robot understand where to go to execute a mission that is more abstract, more challenging, but also eventually more useful to you? So an example mission is we want to command an aerial robot to inspect a part of our infrastructure, to detect how well it is, in what conditions, if there is a structural compromise, if there is corrosion, and so on and so forth. So we don't know necessarily the model. We don't know necessarily what we're going to deal with. We don't know if there are things that have changed compared to a previous mission, but we want the robot to be able to do all that autonomously. And it relies on localization, on mapping, detection of objects, control, and path planning. The last part that decides the actions of the robot, we call it the path planning module. And there are many other different ways to call things, from formal methods to AI. But in fact, in robotics, we typically discuss with these basic three loops, and there are many different ways to approach the solution for every loop. And configuration that eventually shows everything that I just discussed is this one. The robot moves. As the robot moves, the cameras of the robot move together with it. So the cameras, if I'm the robot and I walk around, then my eyes look further away. As this motion happens, and as the motion of the robot excites also the sensors, then we're able to localize based on the correlation of the data of the sensor. I'm going to explain that afterwards. Then if this is happening, we have an estimate about where the robot is and how the environment looks like. We get the estimate of where the robot is, and we feed it to the controller. Now the controller knows where it wants to go and where it is. So it's going to correct the action to actually go where it wants to go. And if this is also possible, then we also feed the map and the location of the robot to the path planner. And the path planner says, all right, that's the map so far. This is where I am. Where should I go, for example, to explore the unknown environment? Same way that you enter this room, and it's so seamless for you to understand it and find where to sit. Consider a robot that wants to do this simple task, find where to sit in this room. So it tends to find an empty spot, an empty seat. So the research activities of the lab span in different directions.
In this video, we present preliminary work on exploration mapping and visually divergent environments using aerial robots.
So I mentioned that we are spanning different directions, and also we try to narrate our videos for the benefit of the community. So we do autonomous navigation and exploration. That's one main thing of our research. The second topic is about multimodal localization. We are very good with just our two eyes and our ears and our inertial understanding of the world. But consider you enter a completely dark environment. The only way for you is to have a torch. For robots, there are also much more accurate ways. Consider that you fly in a brownout. You have to be able to localize also in a brownout. Consider that you ski. It's very challenging for you to localize accurately in this environment. We expect from robots to be able to 3D map as they go through aggressive motions. Consider that you enter an environment with many people around you, and you still want to map, and you want to understand all the agents that are moving, so other pedestrians or other cars. So we work in a topic called multimodal localization. It's all about fusing more sensors, LiDARs, cameras, inertial sensors, GPS when available, into a sensor fusion pipeline to derive a better map and better estimation of location. And our research is all about GPS-denied cases, when GPS is not there. Because A, it's not always there. For example, we do missions indoors. If you fly close to a bridge, GPS cannot support you. And third, GPS might intentionally not even be there because somebody is trying to spoof the robot. So there are many reasons to work in GPS-denied approach, and this is the main trend of research, I would say, in robotics now. And then, of course, robot control systems. In terms of platforms, most of our research has been on aerial robotics, and we now move to ground systems and intelligent transportation, as well as other systems like marine robotics. And in terms of application, I will say the classical example is infrastructure inspection. We have a project together with colleagues from Carnegie Mellon about inspection and monitoring of nuclear sites. This also involves radiation mapping, and you can also have other applications. I have worked in search and rescue, environmental monitoring, and several other applications for aerial or ground robots. So more or less, our motivation spans from the research direction to the platform to the specific application. And I will just take this example for today. I will just pick one of them, the problem of autonomous exploration for a robot, in order to introduce you how a robot actually works and what runs inside, behind the scenes, behind what you saw today in the live demonstration from my students. So consider this simple scenario. The robot enters an environment for which nobody gave it any map, so it has no knowledge. It has to be able to localize itself without the support of GPS, so only based on the cameras, mostly. Number one. Number two, it has to be able to decide where to go to explore an environment that can be complex, for example. And also, it has to be able to fly robustly from A to B in order to achieve this exploration mission. And also further consider that this environment now can be visually degraded, for example, dark, for example, a brownout, and so on and so forth. So even environments that you as a human being, which is much more intelligent than robotics now, you could potentially challenge yourself to do that mission autonomously. So we assume this loop, and we call that the actively closed perception, planning, and control loop. Our research is about to investigate each loop separately, but also the interconnections, how they can connect to each other properly, statistically meaningfully, and through that optimize the performance of the overall system as a whole. So this is what runs on the robot. The aerial robot is just a photo in the darkness. There is a low-level control that stabilizes the robot regarding its orientation, the roll, pitch, yaw angles, for those of you that are familiar. There is a position control that gets the robot from A to B, based on the desired references. As the robot moves, the cameras look around the world. So we have a stereo camera on board the robot. And through that, we map the environment. The data of the mapping and of the location of the robot are fed to the path planner, and the path planner will decide the next best move for the robot to explore the unknown environment. That's the paradigm. That's the way the robot is going to work. The first task is the perception side. So how does the robot explore its environment? How does it map the environment, even when it's visually degraded? And if it's dark, it's meaningful to carry some light with you. Now, it's not so simple for a robot to carry a big torch. So what you see here is the work of one of my students, Frank, who has optimized the system for having two cameras that are synchronized left and right. Through their synchronization, if we get the two images and their calibration, we get the depth map. We get the range against any object perceived from the camera field of view. In the middle of it, you see this red small unit. This is an inertial measurement unit. It has accelerometers, gyroscopes, all of them synchronized with the cameras. So whenever the camera is turning, we also know the rate of turn and also the acceleration of the motion. Then below it, you see a small black unit. This is a 3D laser time of flight sensor. It uses laser beams and a sensor that operates on the corresponding wavelength to get direct range measurements against the environment. These are more sparse, but more accurate compared to the cameras. And on the left and right, you see LEDs. These flash together with the cameras. So every time the global shutter of the camera opens, the LEDs are also illuminating the scene. And the cameras work at 20 FPS, the IMU works at 200 Hz, and the picoflex, the 3D sensor, runs at 5 Hz. So all this system has to be optimized in embedded electronics, and the processing happens only on board the robot. An autonomous robot must not rely on a cloud computer. An autonomous robot must not rely on a laptop computer that you have next to the robot. Everything should happen on board the UAV. And then, after the hardware is there, the research of the remaining of my PhD candidates, Tung and Sheriar, was about how to develop, and Dr. Papachristos, was about how to develop the localization pipeline to allow the robot to estimate its position in this environment and map the environment in 3D, even despite darkness. I'm going to explain that, and you see it in the video. If this is possible perception-wise, then the next question is path planning. And we have two questions to answer. The first one is, if I start from this space and I enter through this particular part of the environment, I only see a small subset. Now, this is a simple room, so there is no big deal to explore it, but consider a corridor. I only see a small subset around me. Then I have to plan my next best action based on the environment I can perceive, and now consider that robots don't have the range of field of view that you have. They typically see more myopically. I have to decide my next best move within the environment I know. And because all the sensor readings are noisy, I have to be able to decide which way should I look at an environment in order to remember it in my map. Now, if you had an environment that on the left side is full of a white wall, and on the right side there are certain characteristic paintings, then you as a human, you will remember the paintings. Now, of course, you are much more advanced than the robot. But the robot has a pipeline in computer vision that finds characteristic patches of the image that can be memorized and can be found, the same ones, in the next camera frame after the robot moved. This process stands for localization and mapping, and through this way, the robot maps the environment. As this relies on the sensor data quality and on the quality of the robot motion, it is probabilistic. We are not certain, we are uncertain about our estimations. So the next goal of the robot is to make sure that not only it explores efficiently, but explores with confidence, so it can remember the map in a meaningful way. This happens in two steps. The robot, within the known environment, it says, all right, I have seen the part on the left. I haven't seen the red part, the pink part on the upper corner, on the right side. So I will try to find a path by spanning all possible directions, probabilistically sense, so a lot of the directions, and identify which direction of motion, which trajectory, will explore more of the unknown world. If I find that, I now have a finite horizon, finite amount of steps, certain seconds, that the robot will navigate to explore the unknown environment. I can decide this mission and execute a small part of it, the same way that you have when you are not certain for something, you do a test and you reassess. So the robot does that in a so-called receding horizon fashion. It estimates for some seconds, and then it will do only one of them, and then it will repeat the same process afterwards. So it will select the next best viewpoint for its exploration. Given that it knows that it wants to go there, it will ask itself, if on the right side is only about white walls, and on the left side, and on the right side have been some very characteristic images, isn't it more meaningful for me, instead of going and looking towards the left side, to first look towards the images I can see and I can remember in my localization pipeline, and then finally orient myself to see towards the unknown space. So I can have a very certain estimation about my motion. And it does so in a second step. This is the first step I just mentioned. So we span this blue tree. We don't span something so sparse, but there is no point in illustrating all the possible directions. Imagine that you just span a big tree, all possible directions around you. You select the green branch, the one that maximizes the exploration gain. So we explore more of the unknown volume. And then you select the first viewpoint to visit. We have a formula for that. There is no point to address a lot about the formula. But what is important is that this is the presentation of the environment. These voxels that you see there, these small cubes, represent if the world is occupied. So if there is an object here, it's going to be all around voxels around it. And the remaining free space will be without any object. So we essentially have a way to classify if this environment is with something in it or if it's completely empty. Then the robot, for example, in this case, should look more towards the right side of the image to complete the exploration of the world. This is the demo that you saw also live at 12 p.m. And then if it's there, if it is in this process of exploring the world, it can remember these very characteristic patches of the environment. So if one of you is the robot, then this nice corner here or this nice corner of the microphone will be among the most characteristic things you will probably remember as a robot. Don't consider it the intelligence of yourself. Within that, the robot will find a way to maneuver in order for its cameras to look towards the most reliable places of the environment from which it can estimate the transformation of its motion. And this is what the robot has to know. The robot has to know its position, has to estimate how wrong the sensors are, so we observe the bias of the sensors, and has to remember the characteristic patches of the environment. I'm going to skip part of the mathematically involved tasks. The only reason I inserted this slide is to invite you students that have interest in robotics to, first of all, study the math behind it. There are two important things here. First of all, to speak the language of the robot, which is programming. The second thing is the mathematical backend behind all that make the robot actually to be able to operate reliably. It's in robotics now, for robots to become ubiquitous, you don't want this particular one heuristic and hack you did at the lab. I'm going to end my presentation with field experiments, because for them to be reliable, we have to have a generic method. And generic method is only backed with mathematics that you have proof that the things can work. So eventually the robot will believe that it's in the middle position and will find a way to go to the next viewpoint by minimizing this bubble around it. This bubble indicates how uncertain it is about where it can be. This is the covariance, representing the covariance as an ellipsoid, and the robot will find a way to go there by making sure that it can be so certain that the bubble around this red spot is quite small. So it will use some mathematical representations to do that. I have this, again, just to introduce more or less the basic steps. So the robot starts from completely unknown environments. It spans a path. It finds the vertex of the tree that maximizes the exploration gain. And then in the next step, it finds the way to minimize the error of covariance. There's no point to go further into the math. Anybody that has a question can contact us afterwards if you want. It's great. So then the hidden hero of all this story is the control system. I forgot to mention so far. But in fact, for all the robot to be able to do these trajectories, the thing that has to be there and work all the times is the control systems. And this has been dealt from the research community in aerospace for years and years. And air robots, typically we can find a control law for them to operate. Other kind of robotic systems like a legged robot, like a humanoid, is even more challenging in certain domains. But the question is what happens when some sort of a fault happens on the robot. So the video that I was playing before showed the multicopter, one of these classical things that you can find also from DJI, losing a propeller and retaining stability. If you go through the math behind the robot, you will see that if you lose one of the motors, you can retain the stability over X, Y, Z, the 3D location of the robot, over roll and pitch, the two main rotations, and you lose the authority regarding yaw. Now, do you want a robot that flew in a crazy way, turning around itself? No, you don't want it. But it can land itself and save the robot, save the people that are around it. So this robustness in control is the critical aspect that will allow society to trust these robots to now operate within our cities without the fear that something can go wrong. And I'm not saying that there is no machine that's always 100% reliably working. But if it's 99.9, then you will never see the problem in your real life. This is an example of the work of some of my people. The robot, and this is the same demo that you saw in our laboratory, it enters this space and knows only what it sees in the first camera view. And afterwards, it selects how to navigate to explore the remaining of the environment. You as a human, you will just turn around. And the robot, without any prescription, without any heuristic, identifies that the best thing to do in an unknown space is turn around to see as much as possible without moving a lot. once the robot identifies that the remaining of the environment cannot be explored if it doesn't go behind the objects that create occlusions, the robot will understand that it has to move on its own further, and from that map the environment. We do that with a methodology called sampling-based path planning, and we augment that with the capability of the robot to operate its planning mission in what is called the belief space, how certain it is about this location, and minimize the localization uncertainty of the robot. This is the second planning step that you saw that happening. This color, red means that we are very certain for a part of the environment. Purple means that we are not very certain. A very bad selection of colors, but this is what it represents. So this video more or less shows the ability of the robot to operate in an environment that is unknown and explore it on its own. Now the question is, Kostas, yes, that works, but this is an easy environment. You have very characteristic colors. It's your laboratory. Good. What happens when everything is in darkness? So this is a robot that used the sensor that I mentioned before, and you will see some flashing. And this is because the robot flashes, illuminates the scene with the LEDs when the camera is opening its shutter. And through that, although in dark in general, the robot is able to operate in this dark environment. The ability of robots to operate in so-called visually integrated environments is the key for them to extend their mission. For example, if you have robots that inspect oil and gas industry, it stands to reason to say that they can inspect while people are not even working there. It's safer, and a lot of that stuff can happen during darkness, during night. And also, what happens if you want to explore something that is, let's say, a warehouse facility? What happens if you want to inspect a vessel after an accident? So you can send the robot, not necessarily an aerial one, but you can send the robot under any condition and do the mission for you. And of course, the mapping is more challenging, but the operation remains autonomous, and the mapping result is derived from the robot in real time. What you see there, and why the map there is a bit more accurate, is because it's using this laser time-of-flight sensor, and the range measurements are much more accurate. So this works also in darkness. Before going to some of the field work, I want to say that I show multicopters, so-called these small area robots, but our experience spans also into different kinds of designs. I want to credit my previous laboratory at ETH Zurich in Switzerland. The video on the right presents a 5.6 meter wingspan UAV that's solar powered and demonstrated 81.5 hours of endurance flight. That's the best kind of endurance that ever was presented from a vehicle below 50 kilos, even gasoline powered or battery powered. That's also the biggest project I have ever worked so far. And it corresponds to an achievement indicating that small UAVs can deliver missions that are very challenging, even for manned aviation. So now you can have a robot that for 81.5 hours, almost 4 days, it operates on its own. And the video on the left side corresponds to, back then, student work, making a robot that takes off vertically and converts to airplane. Crediting them, these guys have made a company. And the new system shows differently. It's a bit more polished and much more capable. But the concept is the important one. It can take off without a runway. It can land without a runway. It can take off from everywhere and land anywhere. And has the efficiency of a fixed-wing UAV. And that's what's important. This hybrid combination is the reason behind this design. So the good thing with UAVs, you don't have the pilot on board. So you can explore many different designs. Now, beyond aerial robots, one also has to consider that a lot of stuff happens on the ground. And with the support of the university and an initiative of the Vice President of Research and Innovation, there is a work here about instrumenting an electric bus of the city with the capability to detect, map the environment, localize the position of the vehicle, detect pedestrians, detect cars, and augment the safety of this system. The next step will be to explore autonomy, but the first step starts from essentially investigating the ability of the vehicle to localize itself autonomously without the support of a human, and also augment the knowledge of the human by telling him, look, there is a pedestrian on your right, although you cannot even see him from the mirror. So this is the bus. We're instrumenting with some sensors up there, and the goal will be to have multiple LiDAR sensors, so laser rangefinders, multiple cameras all around the vehicle. We plan for 12 cameras that are all around, cover all possible angles, several accelerometers and gyroscopes within this vehicle. And you're going to see all the pipeline that we presented before running on small aerial robots, now running with advanced computational capabilities that we can mount on this big vehicle, but also with the insane challenges of a city. And if Reno is small and the traffic is not too much, consider that these systems are expected at some point to navigate in New York or in one of the big cities of Europe. So this means that they have to be able, with pedestrians that just decide to jump on the street because they were pretty lazy at this point, they have to deal with other cars operating in the same environment. Certain assumptions that we do mathematically, one of them that the environment is static, are violated. We know how to deal with them to a certain extent, but then this environment can be very, very different. It can be all cars and all pedestrians all around. Consider that you enter with this vehicle, the campus, with so many students walking around you at a particular time. But this is what makes it interesting. The challenge is what motivates us to do the work for this particular project. Then we had the opportunity to work together with some biologists and Dr. Sudeep Chandra from the biology department for a boat robot that will detect algae in Lake Tahoe. And the goal there, of course, is to make sure that the water ecosystem remains in a good condition. So this was a robotically different project. We have GPS, of course, on the lake. No discussion about GPS denied. But it's all about detecting algae inside the lake. And I have one of my students that works in this particular project. And this is a small video of it. It's a kind of cooler kind of project because you can do the test in a very nice environment. So this is one good reason to exit the lab and go to Lake Tahoe and enjoy the environment a bit there. It's very beautiful. And this boat carries also a stereo system on top with which it can map the shore and make sure that it doesn't crash the shore. Actually, carries cameras underwater. And with a camera underwater, it aims to detect algae. One student, Stephen Williams now, is using a combination of illuminating the scene and tracking a particular wavelength with a camera. And from that, they will detect algae through that way. So we read some biology papers, and we found a way to solve this particular problem. For a robot, the environment, of course, is relatively simpler, right? So there's not really much obstacles around it. So before I stop my discussion about our research, I'm going to end with this title, Robots in the Wild. Nobody wants a robot that works only in the laboratory. It's good for us. You can make a paper with that, maybe. But it's pointless for the society. Robots are supposed to work wherever we want them to work. So this terminology, robots in the wild, represents that they enter our cities, they enter a dark tunnel, they enter a canyon, they enter industrial facility, and we left these environments however we wanted to left them. Nothing was fixed, nothing was static necessarily, and they still operate. So a lot of our work, a lot of the work of my people is about getting these robots in such environments. So this is the work of Dr. Papachristos, my students here, Katak, Frank, and myself, of a robot inside a tunnel at McCarran, operating there. We had no knowledge of the tunnel. It was dark, and it used night vision, near infrared, in order to operate in this environment. If you see this bubble that is up there on the left side, this bubble is how uncertain we are about the location of the robot. The robot is most probably in the middle of this bubble, but can be also somewhere within this bubble. These are the 3 sigma bounds. So this means that having an algorithm that understands how certain the robot is about its localization accuracy, exploit this information to account about how to navigate, means that it can do robust collision avoidance, even though its estimation about its position is uncertain. And you do the same thing. You never have an exact position. So you never really go extremely close to the wall. You perform much more smooth actions. And there is a reason for that, because also nothing is 100% accurate, even for us. And this is the 3D map in a high matrix presentation. What you see there on the image on the bottom left side are the computer vision features tracked from the robot. One comment about one of our projects that works together with the team at Carnegie Mellon is multimodal characterization of nuclear sites. Probably most of you are familiar with the Manhattan Project, all the effort of the United States, and it happened all around the world, about the nuclear race. Now this left a legacy of many sites that are contaminated. And of course, it's very interesting to exploit the idea of using robots in order to help the decommissioning project. And this is funded by the Department of Energy. We have the honor to work with them. And the goal is to enter such environments. For example, a tunnel that is completely dark has chemical waste inside, nuclear waste inside. Send the robot. The robot should be able to do the 3D map, but also what you see down there, detect radiation. And we have the opportunity to work with a very experienced and pioneer of nuclear engineering, Taylor Wilson, who is, he brings the knowledge and the know-how in all that stuff. And also Mr. Ho, that helps us from the radiation safety aspects and also all the experience with radiation sensing in the university. We are not experts in radiation, and that's actually what motivates us even further, because now we can use robots to do a mission for which you typically had to have people that are experts in the particular domain. Once we are able to bring the technology on the robot, we are going to make the possibility of the decommissioning project safer to the humans. Of course, they will have to be there at some point, but then we provide data to them for them to automate and simplify the process. Now, beyond research, there's something fundamental in university education, and I had the opportunity, with the support of my department, to create courses around these topics. which first of all give me the ability to interact with students that have motivation to work with robotics, but also to develop this know-how in our university. So we have these courses as a lab. There is one, Introduction to Aerial Robotics. The goal is certain. You're going to learn about perception, planning, and control for aerial robots, period. It's mostly with a combination of exams and projects, but there is another course, Autonomous Mobile Robot Design. There's going to be no exam. And we did it also last fall. And it's all about getting the knowledge about these fundamental loops, so how the robot localizes, maps, controls itself, path plans, create a user interface so to be able to communicate with you. And then you do this project in your class. The boat project that you saw there operating inside Lake Tahoe was developed as part of this course, which is also a good indication that people here have the ability to develop such systems. Then there is another course which is called Flight Coordinator, happens together with In Situ, and it's about the operational aspects, so how do you use a UAV in the real field. And beyond that, there are seminars bi-weekly happening in our university, hosted by our lab, and it's about a topic. So there have been seminars about UAVs, seminars about human-robot interaction, and so on and so forth, as well as outreach for some of you that are students, high school, or from the community. And this is very important because robotics are not for the lab. Robotics are about how they can change society in a positive manner. Last thing, our facilities. So we had the ability to develop here what we call the Autonomous Robots Arena. It's, by itself, it's not something necessarily useful. It's a big space that provides all the room for robots to be tested. But beyond that, it has a tracking system called Vicon. The company is called Vicon. And then it provides sub-millimeter, sub-degree accuracy of what's the robot location in it. Now, relying on this system is cheating research. So we don't want to rely on it. But comparing your data with Vicon and saying how accurate your robot is about its map or about its location against the ground truth is very important, number one. Now, you documented you are reliable against your peers in the research community. And second, safety, so that it gives you the ability to do something risky, because that's what research is about. It's about testing a new algorithm, testing a new approach. So we can test a new approach, and if something goes bad, this system will take over and handle the safety of the robot and land it. That's the vision, that's what we developed, and this system is installed at the Applied Research Facility of our university with the support also of the university here in the administration. It's open also for other people that want to come and do a test. Contact us, let us know, and you can come and bring your robot and do a test inside this facility with all the support of the infrastructure I mentioned before. Last thing of the research, open sourcing. It's robotics have, I believe it's a even more interesting field because the people there have the spirit to open their code. You know, research was all about only your citations. Now it's also about how many people are using actually your code. Because if people are using your code, means that you did something actually useful. Means that not only you proposed the way that sounds good in a paper, not only you presented some results in your laboratory, but you created a way that people can download your code, compile it, and then run it on their own robot. So there is an infrastructure, or there's a way called Robot Operating System, a middleware, that allows people to develop code and then share it to the community, and then this is transferable to other robots. And we support these efforts now and also before in our research path so far, allowing people to get our code, use it. And this is also what we do with them. Because for progress to happen fast, you have to be able to use the best results of the community. And this is very good in the research world of robotics, that this approach, this trend is there, and many people will try to open source their code. Now I want to close again, mentioning the people that work at my team. Each one of them, the senior researchers, the PhD candidates, the graduate assistants, as well as the undergraduate researchers, all of them are the key components for everything that we present today. Our lab exists for a year in the university, and commending their work, it has been very good and it has been a joy working with them. The results are positive, and we like to invite more students and more people that feel that robotics is one of the things they want to work, or the thing that they want to work, to come and join us from now on. Thank you very much.